звук. Меня слышно? Слышно? Хорошо. Okay, so actually there is only one statement that we need to prove to end this section. And so the section about integral extensions and localizations, and the statement is the following. So proposition. So we're going to need this later. So suppose we have integral extension S over R. And also suppose that we have two prime ideals. So we have prime ideal Q sitting inside prime ideal Q prime, and that is in the ring S. So then the statement is, if we have the following, if you take R and intersect this with the Q, and this is the same as R intersect with the Q prime, right? So these are now two prime ideals in the subring R. So suppose that these two restrictions or pullbacks coincide, then we can conclude that actually these two ideals Q and Q prime are the same in the ring S. So in the statement we don't say any localization, but we're going to need localization in the proof. So first of all, we know that the extension, let me first say for shortness of the notation, P is the R intersect with Q, or the same thing as R intersect with the Q prime. So that's a prime ideal in the ring R. So then the localization SP over the localization RP is again integral extension. That's something that we already proved. So localization of integral extension is an integral extension. And the next observation is the following. Well, if you take now RP, intersect this with the Q SP, I claim that this is the same thing as the RP intersect with the Q prime SP. Do you see why this is so? Well, essentially you take this, and you know the localization, since localization is exact, it preserves intersections. So by this property you get this. So these two things coincide. And moreover, you can also say, if you just look again at the definition of the prime ideal P and localize this again at P, then what you'll get, for example, if you localize the right-hand side, that will be the same thing as this. But if you localize the left-hand side, what you get is PRP. So in this local ring, well, in this local ring, which is the localization RP, we see that we have unique maximal ideal PRP. And this means that these two ideals are also maximal. So these are maximal ideals. Okay. On the other hand, clearly we have the following, that Q SP sits inside Q prime SP. Right, so if you have an embedding like this, localization is again exact, it reveals immediately this inclusion. Well, remember we proved another property that whenever you have a situation where we have two ideals, right, like this, with such embedding, and you know that the intersection with the subring for integral extensions are maximal ideals, you can conclude that these two ideals are again maximal. So these are maximal again, ideals again. So this is also inclusion of maximal ideals. Well, but since these are two maximal, they have to coincide, of course. Right, so you can just that this ideal is maximal and the second ideal is proper ideal. so that has to coincide. But I claim that from this immediately you conclude what you want, that the Q is the same as Q prime. Is the last step clear? Yeah, so exactly. You take pullbacks again, so pullbacks are saturations of Q and Q prime, they are prime, so the saturations coincide with the ideals, so we get this. Okay, so now I'm going to start next section. So this is 7.3, and this is going up for integral extensions. Okay, so first of all, I need to formulate what's the property that is called going up. So the definition is kind of long, but we're going to see how to interpret this in a much shorter way. So take a ring map. So now this is just a general ring map. And we also need to fix two prime ideals. So let's call them P prime and P. So these are primes in the ring R. And also we choose a Q prime. So this is in the ring S. So this is prime over P prime. Sorry, I want to open the window. Okay, so take two ideals in the ring R and also fix an ideal Q prime over P prime. Well, what it means over? Well, this precisely means that the pre-image under the map F, so F inverse of the Q prime is exactly P prime. So the terminology again is a little bit geometric. So if you think about that, if you have a ring map F, so you have a map of specs in the other direction, so you kind of think about this as you have a spec R, and above this there is spec S. So now if you choose a prime ideal P prime, so that's kind of point here, and you're just choosing a point in this space. So this is why it's called lying over P prime. Okay, so if you have this situation, so we have two prime ideals and you choose ideal Q prime over P prime over the smaller ideal, then we say that F has going up property if there is another ideal, so which we're going to call Q, of course. So that's another prime ideal in the S, with the property that with the property that first of all, so such that first of all, of course, we need to Q prime to be inside Q, and of course another property is that Q is over P. So Q is lying over P. Well, to think about this as going up, you need to think that you have P prime and you organize your chain of two ideals like this. So this is in the ring R, so then somehow if you know how to choose an ideal lying over P prime, that is Q prime, well, you need to be able to choose an ideal Q, which is in this picture above Q prime, and also under restriction corresponds to the given ideal P. Okay, so maybe something like
All equations are strict and
all ideals are proper, of course, unless we say that's a unit ideal. Inclusions are strict because if the inclusions are not strict, that's not a very interesting definition. Well, you know, if these two things coincide, well, you know that you have a way to choose Q prime, you just choose Q to be the same. So there is nothing to worry about. Okay. Well, an important observation is that, well, you can reinterpret this geometrically. So F has going up property if and only if you consider the corresponding map of the specs. So you have spec of the S modulo Q prime. This is mapped to the spec R modulo P prime. Sorry, not Q prime, P prime. Right, so this map you automatically get because we have the corresponding map for the rings, right, since you have this property. Now, this has going up property if and only if this map on the specs is surjective. Which, if you think about what you have other prime ideals in the by the correspondence theorem in the quotient rings, that's exactly the statement that we have here. Okay. Before we prove anything, I have several trivial remarks. So first remark is that by induction, so we can replace two ideals by a finite chain of ideals. So we have a chain P1 sitting inside P2, sitting inside up to some ideal Pn. So this is a chain of prime ideals in the ring R. So then if you have a way to choose a prime ideal Q1 lying over P1, so this is lying over, and so then you can continue this chain and get a chain of the same length of prime ideals in the S. Clearly, these two properties are equivalent, so if you have this, you just restrict your attention to n is equal to 2, and if you have that definition, you just do induction by the lengths. So this is one trivial remark. And the second trivial remark is that if you consider composition of two maps, so 2, so if F is a ring map from ring R to the ring S, and there is another ring map G from S to T. So if these two maps have going up, then the composition, so composition GF from the ring R to the ring T also has going up. So let's say this is true. If these two maps has going up property, then the composition also has going up property. Yeah, for example, yes, if you have such a situation where you know that the going up property is true, you have this. Okay. Proposition, and now we have an actual geometrical interpretation of this going up property. So going up holds for some map, say let me call now this is phi, or to the S, if and only if the induced map, so let me call this capital phi, which is the same thing as the spec of phi, so that's a map on the specs, so the induced map on the specs is closed in a topological sense, meaning that the image of a closed set is a closed set. Proof. Okay, so let's suppose that going up holds for this map, so we're going in this direction. So we need to take, so let's take an ideal J in the ring S. Right, so I want to show that the map capital phi is a closed map. So meaning that if I take a closed subset in the spec of S, so I take an ideal and I consider the corresponding, so what's the goal? We want to show that if I consider capital phi applied to the V or J, well, somehow I need to show that this is V of some ideal I, where ideal I is an ideal in the ring R. Right, so that's the goal. If I can show this identity for some ideal I, that's what I have in this statement. Okay. Well, first of all, we have another kind of trivial observation. If you have any surjection, so in this case, this surjection is S to the S modulo J, then for surjection, going up holds, clearly by the correspondence theorem. So any surjection has going up property. And now I know that the composition of two maps that satisfy going up property also satisfy the going up property. So in this case, my composition that I consider is R to the S, which has going up property, and then I compose this with the map to the quotient. So this also has going up as composition. Okay, so now I can just abbreviation want to show. So this is what we want to get. Well, this is our goal in this proof. So definitely, if we can show this, then this means that the map phi is closed, mapping any closed set to some other closed set. Okay, so now I want to introduce this ideal I. So in fact, I that we can take is the kernel of this composition. So don't want to give a name to this map, so but this composition is here, and the kernel is some ideal I in the ring R. So if I introduce just I like this, say I, this is by definition, then I have extension of rings R modulo I is sitting inside S modulo J automatically. Okay. Now let's take a prime ideal. So if P is a minimal prime of the quotient ring R modulo I, so then I have the following. So then well, again, I use exactness of the localization, so I localize at this minimal prime ideal this inclusion. So I get that R modulo I localized at some minimal P. So this sits inside S modulo J localized at P. And I know definitely that this localization is not equal to 0, since localization of the ring at any prime ideal is not equal to 0. So, but this immediately means that if this is sitting inside this ring, so this means that this ring can be 0. So this ring is not 0. This is what I want to know. Now, let me take some prime ideal in this quotient and then localization by P. So this is a some prime ideal. So we know that if this is a non-zero ring, at least we have maximal ideals, so I can guarantee that there are prime ideals here. So for example, maximal ideals. So then I can combine two correspondence theorems, correspondence theorem for the localization, correspondence theorem for the quotient, and by these two theorems I can conclude that the ideal J is sitting inside ideal Q, and this is sitting inside ideal P. So it's a little bit abuse of notation. I think about the ideals Q in the localizations as prime ideals in the S modulo J that is contained in the P. But I also can think about this ideals Q in the S modulo J as prime ideals in the S containing J. So here I can think about this Q as actually a prime ideal in the ring S. So ideals here in this quotient, the localization corresponds bijectively to the prime ideals in the S with these two inclusions, satisfying these two inclusions. Okay, so what happens if I take this prime ideal Q and then I intersect this with the subring R modulo I? So do you see what the answer will be? Well, first of all, that's a prime ideal, right? So that's a prime ideal. Now, if you just look at this inclusion.
Okay, it's P is minimal.
Yeah, so this is a prime ideal, and this will be sitting again inside the intersection of the P with this thing, but it's exactly P. So, and this P is minimal. So this intersection is P. Okay, so but what it tells us? Well, it tells us that if you consider the corresponding maps on the specs, so map induced on the specs, so spec S modulo J mapped to the spec R modulo I, right? So I'm getting this right. So this is map of the specs for this inclusion going in that direction. So what we can say, we have the following. I take any minimal prime here, and I can see that any minimal prime is kind of in the image of this map. So this map hits all minimal primes of the spec R modulo I. So any minimal prime is in the image of the corresponding map on the specs. Well, now we have the going up property, right? So the going up property is still satisfied for this map. Well, because it's satisfied for this map, and then you just use the correspondence theorem. So the conclusion is that by going up, you can say that the corresponding map here is surjective. So spec S modulo J to the spec R modulo I is surjective. Right? Because, well, you take any prime ideal, or you want to know that any prime ideal is in the image of this map. Well, take a prime ideal, it contains some minimal prime ideal, and apply going up property for this pair, and you already know that there is an ideal lying over this minimal prime. Okay. Another thing that you already know from the very beginning of this course, that this spec is isomorphic to the V of J, and this spec is isomorphic to the V of I. So on this closed subsets, we have the surjective map. But that's exactly what we need to prove here. So this finishes the proof in one direction. In the other direction, it's actually easier. So now we know that capital Phi is closed. Well, we can remember that we, again, in the very beginning of this course, we proved the following property, that whenever you take V of I, you apply spec of some map. This is the same thing as the V of the I inverse of the ideal. Right, so that was a general property. Well, if I add closure here, right, so that's something that we proved on the seminar, but now since I know that this map is closed, I don't need the closure here. So this is just a property that is true without closure. And if you just plug into this formula, I think that was one of the problems on the first quiz. You just need to take this formula, you just need to remember this formula, and plug into this formula the special case, well, where you take I to be Q prime. So I in the first formula is Q prime. Right? But if you have this exactly means so that the map on the spec S modulo Q prime to the spec R modulo P prime is surjective. Right? Since we know that in the prime ideals in these two specs are exactly the same as prime ideals in these two V's. Okay, that's the end of the proof. So now we have the following theorem that actually has a special name. So this is called the lying over for integral extensions. So lying over. So that's another property that is true for integral extensions. So if S over R is integral extension, then the map of specs, so then spec S is mapped to the spec R, so then this map of specs is surjective. Okay, fix a prime ideal P in the spec R. So then essentially everything follows from the following commutative diagram. So you have an integral extension R is mapped to the S, so this map is just an embedding of R as a subring in the S. And then you have a canonical map to the localization, so let's call this iota RP, so this is to the localization RP. And then have canonical map to the localization iota SP, this is to the localization SP, and there is a map between the localizations. Okay, so using the same reading as before, so here this was the argument. So I want to say that the localization is not zero. So I want to say that this localization is not equal to zero. So localization SP is not equal to zero. Well, since inside this localization I have this subring Rp which is not 0. Well, since Sp is not 0, there is, for example, maximal ideal in the Sp. So M in the M sitting inside Sp is some maximal ideal. Now let's look what we can see if we just look at this maximal ideal and commutativity of this diagram. So take this maximal ideal, we can pull back along this map. This will be again a maximal ideal in the Rp. Well, we know this property that this is property of integral extension. So this is since integral extension, if this is maximal, then the pullback is again maximal. We proved this last time. So in general, we can say this is just a prime ideal, but for integral extensions, we know this is maximal. So this will be a maximal ideal here. But let's write this. So Rp intersect with M, that's a maximal ideal, but here we have unique maximal ideal. So this is P Rp, right? And under this canonical map to the localization, iota R, well, we know what the preimage of this unique maximal ideal is. Well, this is exactly the prime ideal P. So, and if we take preimage iota inverse, well, I don't know how to write this, iota R P and then inverse of the PRP is P. Okay, so we see that if we start with the maximal ideal, going like this, with these two maps, we are getting back prime ideal P. And that is true for any prime ideal P. But if you go using the other two arrows, well, we get, first of all, the preimage. So let's say that the Q is the preimage under the map iota SP of this maximal ideal M. So Q here is actually some prime ideal lying over M. But if I take preimage, well, the preimage is just intersection, so R intersect with Q, I again get P. Right, since when I go like this or I go like this, I'm supposed to get the same prime ideal. So I have a prime ideal Q such that its preimage is P. But that's what I need to show, right? I need to show that the map is surjective. So for any prime ideal here, I have constructed a prime ideal Q in the S such that its preimage is exactly P. Well, this is property of the integral extensions. So we know that the localization of integral extension is integral extension, and we know that whenever we consider prime ideals, so if you take a prime ideal here and then take intersection like this, then this is maximal if and only if the intersection is maximal. And here we have unique maximal ideal. So since we know the intersection is maximal, it has to be this thing because there are no other maximal ideals in the localization. No, that the property that in the Rp there is only one maximal ideal. This is a property that, well, yeah, property of, well, the statement is when you localize at the prime ideal, you get the local ring. Yes, that's a property of the localization. Okay, next theorem, which is more or less trivial, but it still has important applications. So this is statement that going up is true for integral extensions. So this is the reason why we study this property, property going up in the chapter about integral extensions. So if S over R is an integral extension, then it satisfies the going up property. Well, this follows more or less immediately by our interpretation of the going up property as the property that the map on the specs is surjective. So you do the following. You consider R modulo P prime, which is mapped to the S modulo Q prime. Right, so whenever you take any prime ideal in the S, which is Q prime, and the P prime is just R intersects with the Q prime, you have a map like this, which is again an integral extension. Well, but for integral extensions, you know that the map on the specs is surjective. That's it. That's it. So by lying over the map of the specs is surjective. And that was the interpretation of the definition that I gave exactly after the definition. So that proposition that having going up property is equivalent to the property that the map on the specs is closed, it was more or less for your general education. Doesn't really need, they don't really need this proposition to prove these properties for integral extension. I don't use it anywhere. I just decided to include this as a nice geometrical interpretation of this algebraic notion. Okay. So that was section 3. Now let's do some applications of these notions. So this is 7.4, algebras of finite type. Say over a field. So I start with this definition, which I'm going to use in the next proposition, but I think the definition is quite kind of naive and expected. So you take an algebra, so A is an say R algebra, and you take several elements, so x1, x2, xn. So these are elements in the algebra A. So these elements are algebraically independent. Or you just need to formalize the idea that there are no algebraic relations between these elements of the algebra. Well, how you can do this? Well, you can, for example, consider the polynomial ring. So that's algebra over R. So we consider polynomial ring over R. I introduce as many variables as I have elements. Then I have a canonical map from this polynomial ring to the algebra, right? Just sending the corresponding variable to the element. And if I want to say that these are algebraically independent, well, meaning there are no relations between these variables, well, I can say that this is an embedding, so there is no kernel. So if map has trivial kernel, that's exactly the statement that there are no algebraic equations relating these elements. And now we have theorem. which is called Noether normalization. So I think it is called Noether normalization lemma, but it's quite an important statement, so I decided to call this a theorem. And the statement is the following. You take algebra A is an algebra of finite type over a field. So an algebra of finite type over a field, and let's fix notation for the field. So some field K. So then there are algebraically independent elements x1 up to xn for some n in the algebra A, such that if you consider, well, such that the extension is integral. So the extension, when you consider polynomial algebra, right? If this is algebraically independent, then this algebra is just this polynomial algebra embedded in the ring A. So, and any other element in the given algebra of finite type is just an integral element over this subalgebra. So I think this is quite a powerful theorem. It says that if you have any algebra of finite type over a field, you can study this as an integral extension over a very simple algebra, just polynomial algebra. Okay, so the proof kind of consists of two parts. So in the first part, I want to describe a change of variables that is useful in this proof. And then in the second part, I'm going to do this change of variables and actually prove this statement.
What is n at this point?
N? Well, there is some n.
Isn't it kind of true, because we can take n equals 1 and just take any number?
No, that's just not true. For example, if you take a polynomials in two variables, you cannot say this is an integral extension of polynomials in one variable. Well, why? If you have x and y is algebraically independent with x, so it's not integral of a polynomial in one variables. So in general, we can just say that we can choose such finitely many elements that this is true. Well, in some cases, n could be equal to 0. Right? If you just consider the extension of fields, which say finite extensions, well, clearly everything is satisfied, but n is equal to 0. Okay, so first of all, I can do the following change of variables. So we're going to see why this is so helpful in several minutes, but let me just describe formulas. So here, change of variables, or if you want to be more formal, you can say change of the generators of an algebra. So this is a polynomial ring, and again, n variables. So then you can introduce new variables. So you can say that y1 is just the same thing as x1, then y2 is x2 minus x1 to the n. So this capital N is at the moment is just a parameter. So you can do the change of variables for any positive integer n. And etc. You just continue changing variables like this. Y with the index n is xn minus x1 to the large n to the power n minus 1. That's the general formula for change of variables. Well, clearly you can see this is invertible change of variables. Right? Whenever we start with a polynomial which is written in terms of variables x, so say f is such a polynomial, so then you can rewrite the same polynomial, so x xn, as well. Of course, the polynomial will be different, g, but in terms of variables y. That's invertible change of variables, so we can write any polynomial in x's as a polynomial in y's. Okay. If I, for example, consider monomial, so x to 1 to the sum r1, and take the product xn to the rn, and I do this change of variables. So instead of all the x's, I need to write expression in terms of y's. So then I claim that I get the following. So I'm interested in the leading term in terms of y1. So I'll get y1, which will be to the power r1 plus r2n plus etc. up to rn capital N to the power n minus 1. And there will be other terms, of course. But if I take n sufficiently large, then well, this thing is the leading term. So you can do this kind of elementary computations with polynomials and powers of these polynomials and monomials and convince yourself this is a leading term. So for example, I think it's enough to take n to be strictly larger than the total degree of the polynomial f. So, and why this is helpful? Well, because you can do change of variables, and you kind of have one distinguished variable. In this case, this is y1, such that you can control the leading term if you have any polynomial. So here you have all the variables, so the coefficients will be just a constant. So the leading term will be some expression in y1 times some constant. So it means that when you consider polynomial in y1 and all other coefficients being just kind of, all other variables being just coefficients, you get an equation of integral dependence, because if you have element from the field, you can divide by this element. So this is why this trick is important when we discuss integral extensions. Okay, so that's the general observation about the change of variables. Now, let's prove this. So let x1 up to xm be generators of A. This is an algebra. This algebra of finite type. Remember that this means that it's generated by some finitely many variables, and maybe there are some relations among these variables. So without loss of generality, we can assume that x1 xn are algebraically independent. Right, so choose algebraically independent elements in this set, and maybe you need to do some reordering, but you can assume that the first n are algebraically independent. So then you have the rest. Again, it is possible that n is equal to 0. So then, of course, I can trivially observe that if I consider these xn's and also add one more variable xi for any I greater than n, then these are algebraically dependent. So the proof is by induction on m minus n. So on how many generators we have if we exclude the algebraically independent generators. So m minus n. So the base of the induction is the case when m minus n is 0, so m is equal to n. Well, but in this case we're done, because it means that we have m generators, and these generators are algebraically independent. So that's the case when A is equal to this polynomial algebra. So the base of the induction is clear. Now let's do the step of the induction. So first of all, I know that if I consider, say, elements from x1 up to xn plus 1, then there is an algebraic equation relating these elements. So there is element f in the polynomial ring in n plus 1 variable. So this is supposed to be capital X's, just some variables, such that if you plug in x1, x2, up to xn plus 1, you'll get 0. Right? So first n are algebraically independent. If you consider the next one, there is an equation of algebraic dependence. That's an equation of this algebraic dependence. Now I do the change of variables, so I can take this f, and instead of variable x, I can use variable y plus 1. Right? And so this is change of variables. Well, I need to be a little bit accurate here. So I want the leading term with respect to the n plus 1 to be constant. Right? So because I want the equation of the integral dependence for the last element. So this means that essentially I'll do the same of change of variables, but I kind of switching the indices in the other order. So this will be xn, yn is equal to the xn, etc. So by do the change of variables, and I can claim that the leading coefficient, of G well, with respect to variable yn plus 1 is constant. So what I have here is the following. Instead of x's, I can use y's. So I can say that A is generated by y1 up to yn. Then I have yn plus 1. And then I have x's. I didn't do anything with the x's with the indices n plus 2 up to m. So still I can use this as generators, and also I can see that yn plus 1 is integral. So this is integral over polynomial subring generated by the y1 up to yn. So algebra A is integral over subring generated by y1 up to yn, and then I can skip yn plus 1 and just use xn plus 2 up to xm. And that's the step of the induction, because here you can see that m minus n is less by 1. So this is the end of the proof. So that's a so powerful statement that the rest of today's lecture and probably part of the next lecture, we're going to be deriving some corollaries from this. So the first corollary is the following famous theorem. Well, sometimes this is even called the Hilbert-Null-Stalin as some very weak form, but I'm going to call Hilbert-Null-Stalin as another statement. So here again, A is an algebra of finite type over field. So is an algebra of finite type over field K if A is a field, then A is a finite extension of K. So in the sense of the field theory, finite as a vector space over field K. Okay, so in the proof we need to consider two cases. Well, first of all, we already know key observation is that we have this integral extension for some n. Well, let's consider a special case when n is equal to 0. So then what we can say that A is integral over K and of finite type. And we proved the general theorem when we discussed integral extensions that being integral and of finite type just is the same thing as being finite. So A is finite, so finite over K. Finite as a module, K is a field, so that's a finite dimensional vector space, that's a finite extension of fields. So this case is completely trivial. How about the case when n is positive? Well, I claim that it's even not possible to have such a case. I'll consider a prime ideal generated by all these variables. Right, so that's a prime ideal in this subring. By lying over, there is a prime ideal Q. So by lying over, there is Q, prime ideal in the A, such that if you take Q and intersect with the subring, in this case, which is just a polynomial ring, you're supposed to get P. Right? Now A is a field, so Q is 0, P is 0. That's a contradiction. And this is the end of the proof. So the first case is kind of trivial, and it is not possible to have any other cases than the first case. Okay, corollary. Again, A, let me just say as before, finite type over a field K. And we take M in the A to be maximal ideal. So then the quotient A modulo M is a finite extension of K. So the proof is really just one line. Well, we know that A modulo M, since this is a maximal ideal, this is a field. But if you take a quotient of an algebra of finite type, there's still an algebra of finite type. So we just apply previous, what was this theorem? Yeah, previous theorem. So A modulo M is a field, and A modulo M is of finite type. Again, over the same field K. So, by previous theorem, we're done. Okay, next corollary. That is something that I promised in the chapter about Argenian rings. So A as before, and also Argenian. And then dimension of A over K is finite. So when we discussed Argenian algebras, Argenian rings, actually we saw that there are examples which are Argenian algebras, which are well, algebras over field K. And if this is finite dimensional as a vector space, clearly this is Argenian, right? Because, well, ideals are subspaces, vector subspaces. So one direction is completely trivial, but the other direction is also true, but of course we didn't have the tools to prove this in the chapter about Argenian rings. So now we prove this. So if you combine this corollary with what we already know, we could say that if algebra, say algebra over a field of finite type is Argenian as a ring, if and only if it is finite dimensional as a vector space. Okay, so first of all, by the structure theorem for Argenian rings, remember that the structure theorem for Argenian rings is just a statement that any Argenian ring is a product of local Argenian rings. So by this structure theorem for Argenian rings, it is enough to assume that A, say with some maximal ideal, is local. Right? If you can prove this for any product that is finite dimensional vector space, clearly the product of algebras will still be a finite dimensional vector space. Okay, so we can assume this we will work with the local Argenian ring. Okay, so now what we already know, that if we take this A modulo M, well, that's a finite dimensional vector space. So is finite extension of K. And also another observation, that if you have a local ring, this is unique simple module. Remember that any simple module is a module of the form ring, in this case algebra, module some maximal ideal. So there is only one maximal ideal here. Over a local ring there is unique simple module. But one of the criteria to check that the ring is Argenian is to say that the length, it has to be Noetherian, which in this case this is clear, this is finite type over a field. This is equivalent to saying that the length is finite. But if the length is finite, we have a filtration such that all the quotients are, we have a finite filtration such that all the quotients are simple modules. So we can construct infinitely many steps as taking extensions of finite dimensional vector spaces. So there is finite filtration, say, I don't know, this is A, let's call this, then there is M1, then there is Mn, which is maybe M plus 1, which is 0. All these Mi modulo Mi plus 1 has to be isomorphic to the A modulo M. Right? And then you say that, well, this, for example, doing by induction from the end, you see that Mn plus 1 is 0, so Mn will be finite dimensional. No, this will be just this thing. And then you do, well, what you have. You have short exact sequences where you have Mi plus 1 embedded into Mi, and the quotient is A modulo M. Right? By induction, all these Mi's will be finite dimensional vector spaces. Right? So you start with 0 dimensional, so Mn is fine dimensional, then you do this next step, this will be fine dimensional, this is fine dimensional over k, so this has to be fine dimensional over k, and you finish with the M0, which is the same thing as A, which is finite dimensional. End of the proof. Okay. Okay, another corollary. So now we have F, a map between algebras of finite type. Actually, let this be a map of algebras. Map of algebras over K, and let's assume that B is of finite type, of course over K. Let's take a maximal ideal M in the B. So this is maximal. Then I claim that the pre-image of this maximal ideal in the A is again maximal. So in general, we only know that the pre-image of a prime ideal, or in particular maximal ideal, is again only prime. We saw that there are counterexamples saying that the pre-image of a maximal ideal is not necessarily maximal. For example, Z embedded into Q. Take a 0 ideal in the Q, it is maximal in the Q, but the pre-image is 0 in the Z, and that's just a prime ideal, not maximal. Here you have these additional assumptions that this is a map of algebras, and B is also finite type. It is true that the pre-image of a maximal ideal is maximal. Okay, so let's say that N is this pre-image of the maximal ideal. So what we have then? Well, we have the inclusion K is sitting inside A modulo N, and A modulo N is sitting inside B modulo M. Okay, so what we can now say, well, this thing B modulo M, this finite type, this maximal ideal, so that's a finite extension. So this is finite dimensional vector space over K. Hence, this is a finite extension. So A modulo N is finite over K. Okay, so what then can we say? That's a algebra over K, which is finite dimensional, and clearly this is Argenian. We don't even need this. Well, that's just trivial observation. So any algebra which is finite dimensional over K is Argenian. Argenian. Okay. But this is sitting inside the field. So there are no zero divisors here. That's the domain. Or in other words, you can say that since we know that the pre-image of a maximal ideal is at least a prime ideal, so at least this is a domain. So this is a domain, but remember that for Argenian rings, being a domain and being a field is the same thing. That was one of the properties that we proved. So it's Argenian and domain. And there are no Argenian domains other than fields. Okay, so we proved this. So in other words, if you consider, so for algebras, of finite type over some field K, well, you have a map spec M. That is a map between, well, we used A and B, so this is B, and this is A. So in general, the induced map on the maximal spectrums, well, it's not functorial. So in general, there is no even a map here. But if you consider not all rings, but only rings which actually are algebras of finite type over some field K, you can construct such a map. So that's a subcategory where you can work only with maximal spectrum in the in the factorial way. Okay, definition. So let's take an ideal in the polynomial ring in n variables. So then the point alpha 1 up to alpha n in the affine space of dimension n over the algebraic closure of K is called algebraic 0. Algebraic 0 of the ideal I if f on this point, f of alpha 1 up to alpha n, is 0 for any element f in the given ideal. So you can compute polynomial on any n-tuple of elements of the algebraic closure of the field, and you're supposed to get 0 for any f in the ideal. So that's an algebraic 0 of the ideal. So for example, if the field is algebraically closed, well, you can just take the ideal and the set of algebraic zeros of this ideal. Well, this is just the corresponding kind of V of this ideal, but inside the spec M of this algebra. Not just the spec, but spec M. Okay, so from the ideal, so this I fix an ideal, and I want to say that a point is algebraic 0 for this ideal. Okay, so now we have the following theorem. Yeah, you can interpret this. If you take this algebra of finite type and you try to compute the spec M, well, what this will be? Well, if the field is not algebraically closed, well, the answer could be complicated. We know this, for example, for real numbers. We've done this explicitly. But say over algebraically closed field, well, this will be just this. For algebraically closed field, you can think about this algebraic zeros as just the corresponding V of an ideal, but this V is supposed to sit in the spec M. So all the points where any element of the ideal is vanishing. Okay. So theorem, if you have an ideal I in the polynomial ring in the n variables, so this is an ideal without algebraic zeros. So there are no points as in the previous definition. So then this ideal is actually the unit ideal, or just the ring. Okay, proof. So if our ideal is actually not the unit ideal, well, then there is some maximal ideal. So there is M in the spec, let's say in the spec M of the polynomial ring such that our ideal I is contained in this maximal ideal. Now if I consider quotient of the polynomial ring by this maximal ideal, well, I get some finite extension of the field K. And I know that I can embed any finite extension into the algebraic closure. So there is an embedding theta from the this quotient modulo maximal ideal to the algebraic closure of the field K. Well, now I just set alpha I to be theta of the xi. Or maybe, well, if I want to be more precise, maybe xi plus m, so the corresponding classes. But by this construction, if I compute f on these alphas, take f from the ideal I, try to compute this on these alphas, well, if you do this, this is the same thing as computing theta on the f of the axis. Again, maybe to be precise, I need to say plus maximal ideal m. So, wait. No, I don't need plus m. So I'm just trying to understand what will happen if I take this f in the ring and then I apply I guess it's not very consistent. I guess what I want from the let's say that the map theta, so this is an embedding into algebraic closure, and then the theta will be the composition of the map from the polynomial ring in n variables. Then I map this polynomial ring in n variables to the quotient, and then I embed quotient into algebraic closure. So this makes more sense. Then indeed alpha I is the theta of xi, and then if I want to compute f on these alphas, clearly this is just the same thing as just I need to take this polynomial written in terms of variables and then apply map theta. Okay, but since if I take f in the ideal I, right, so an ideal I, we know that this is contained in the maximal ideal, so this is contained in the maximal ideal, so it means that this composition will be 0. So f of the alpha 1 up to alpha n, this is 0. Since the right hand side is 0. And this means that we exactly constructed an algebraic 0 for any proper ideal. So any proper ideal has an algebraic 0 constructed this way. Okay. So I need to start here, and next time we use this theorem to prove another theorem, the Hilbert-Null-Stalin sats in geometric form. It's one of the famous theorems for commutative algebra.